All right, page 92 in the lab manual. Doppler effect, relativistic redshift, and the Hubble law. This goes to the idea of keeping our eye on the ball. Recall that we started this discussion way back at the beginning of the semester talking about dark matter and dark energy. Dark energy talks about the expansion of the universe and how it is accelerating. To get a grasp on that, we have to understand how it is we know that the universe is expanding in the first place. To do that, we need to understand what the Doppler effect is. And to understand the Doppler effect, we have to have some basics in how waves work. And this works whether it's a sound wave or a gravitational wave or electromagnetic radiation or light. So we'll start with a sound wave. Here we have a 100 hertz wave. 100 hertz, that means 100 cycles per second. We use this schematic of a sine wave to describe a wave. That's a convenient way to describe it. And so this would be one single wave, 100 of them per second. That's a low bass note in case you're interested. And so this would be one complete wave, and we use Greek letter lambda to indicate wavelength. All right, so this is one wavelength of this wave. It takes one 1/100th of a second to go through its one complete cycle. Now we'll compare that with a 200 hertz wave. So it's going to have twice as many cycles, twice as many oscillations in the same amount of time, and we can describe it like so. All right, and as you can see, the length of this wave is half the length of the first wave. All right, and so that goes to a very fundamental idea. If you look at that block on the right-hand top side of your sheet, these are the basic formulas that determine how waves work vis-a-vis the frequency and the wavelength and the velocity of a wave. That's the relationship. So the velocity of a wave is equal to its frequency times its wavelength. Therefore, its wavelength is equal to the velocity divided by its frequency, and the frequency of a wave is divided by its velocity divided by wavelength. And it's important to understand that frequency is inversely proportional to wavelength. Frequency inversely frequency is inversely proportional to wavelength, which it's just a fancy way of saying if one gets bigger, the other gets smaller. If one gets smaller, the other one gets bigger. That's how it works. So just to give an example, the speed of sound, Mach 1, at sea level is approximately 1,100 feet per second. So what would be the wavelength of a 60 hertz tone? That's a low B-flat tone. So what we would do is we'd go wavelength equals the velocity of the wave divided by the frequency, which in this case is 1,100, over the frequency, 60, which comes out to, if you punch it out on your calculator, 18.333 feet. And that would explain why, if you've ever noticed, bass notes seem to carry a lot further than high notes. All you got to do is just sit on your front lawn on a summer evening and listen to a boom boom car come down the road. You hear that boom boom before you hear anybody else. All right. Or if you're in a boom boom club and you have those great big subwoofers, and you notice if you get further away from where the subwoofers are, you can actually hear the bass better. Well, that's because your ear bone is getting the full wavelength by moving further away. All right. So that's our basic intro. Just understand these basic relationships between frequency, wavelength, and the velocity of a wave. We'll pause here and then we'll go to the next page.